Welcome to another thrilling episode of Sci Discovery Chronicles. Today, we're embarking on a journey into one of the most enigmatic realms of science, the quantum world. Picture this, a place where the rules of classical physics break down, where particles behave in ways that defy our everyday understanding. This is the quantum world of photons, where light isn't just light, but a phenomenon that challenges the very fabric of reality. Join us as we unravel the strange dual nature of light, a journey that will take us through the heart of quantum mechanics, revealing the incredible properties of photons, light's most fundamental particles. Section 1. The nature of light. For centuries, light has been one of the most captivating mysteries in science. What is light? Is it a wave? A particle? Both. The answer to this question has puzzled great minds from Isaac Newton to Albert Einstein. In the 17th century, Newton proposed that light was made up of tiny particles, or corpuscles, while at the same time, Christian Huygens suggested that light was a wave. These two theories seemed mutually exclusive. How could light be both? It wasn't until the early 20th century that this paradox was partially resolved through the development of quantum mechanics. Scientists discovered that light exhibits a strange dual nature. It behaves both as a particle and as a wave, depending on how it is observed. This concept, known as wave-particle duality, is one of the cornerstones of quantum mechanics and fundamentally changes how we understand the universe. Section 2. The particle nature of light. Photons. Let's dive deeper into the particle aspect of light. When we talk about light as particles, we refer to photons. Photons are elementary particles, the smallest units of light, which carry energy but have no mass. They travel at the speed of light, about 299,790 kilometers per second in a vacuum, making them the fastest entities in the universe. Each photon carries a specific amount of energy, determined by its frequency. The higher the frequency, the higher the energy. This is why ultraviolet light, with its high frequency, is more energetic than visible light. But here's where things get even more interesting. Photons don't behave like classical particles. Unlike tiny billiard balls, photons exhibit quantum behavior, meaning they can exist in a superposition of states and can be entangled with other photons. Section 3. The wave nature of light. Now, let's shift gears and explore the wave nature of light. When we think of light as a wave, we imagine oscillating electric and magnetic fields propagating through space. This wave model explains many of the phenomena we observe, such as interference and diffraction. The famous double-slit experiment vividly demonstrates the wave nature of light. In this experiment, light is shown through two closely spaced slits, creating an interference pattern on a screen behind them. This pattern, characterized by alternating light and dark bands, is a hallmark of wave behavior. Waves from each slit overlap, reinforcing or canceling each other out. But here's the twist: when individual photons are sent through the slits one at a time, they still form an interference pattern over time, even though they arrive at the screen as particles. This mind-bending result suggests that each photon somehow passes through both slits simultaneously as a wave until it is observed, at which point it behaves as a particle. This is the essence of wave-particle duality. Section 4. Quantum superposition and entanglement. The quantum world doesn't stop at wave-particle duality. Another mind-boggling concept is quantum superposition, where particles like photons can exist in multiple states simultaneously. Imagine a photon that can be both in a horizontal and vertical polarization state at the same time until measured. Upon measurement, the photon collapses into one of these states. This phenomenon lies at the heart of quantum computing, where bits can exist as 0, 1, or both simultaneously, vastly increasing computational power. Even more puzzling is quantum entanglement. When the photons become entangled, their states are linked no matter how far apart they are. A change in one photon's state instantly affects the other, even if it's on the opposite side of the universe. Albert Einstein famously referred to this as spooky action at a distance. Entanglement challenges our classical understanding of cause and effect, suggesting a deep, underlying connectedness in the universe that we are only beginning to understand. Section 5. The role of observation, the Copenhagen interpretation. So, what does it mean to observe a photon? In the quantum world, observation plays a crucial role. According to the Copenhagen interpretation, one of the most widely accepted interpretations of quantum mechanics, a photon exists in a superposition of states until it is observed. The act of measurement forces the photon to choose a state. This concept is famously illustrated by Schrödinger's cat thought experiment, where a cat in a box is considered both alive and dead until the box is opened and the cat's state is observed. In the case of photons, they exist in all possible states until observed, at which point they collapse into a specific state. But what exactly constitutes an observation? Is it a conscious observer, a measuring device, or something else entirely? This question remains one of the greatest mysteries in quantum mechanics, and scientists continue to explore its implications. Section 6. Practical applications of photons. You might wonder, how does all this abstract quantum theory affect our everyday lives? The answer lies in the incredible practical applications of photons and quantum mechanics. One of the most groundbreaking applications is quantum computing, where photons are used to create qubits, quantum bits that can perform complex calculations at speeds unimaginable with classical computers. Quantum computers have the potential to revolutionize fields ranging from cryptography to medicine, solving problems that are currently intractable. Another exciting application is quantum cryptography, which uses the principles of quantum mechanics to create ultra-secure communication systems. Since any attempt to eavesdrop on a quantum communication channel would disturb the photons and be immediately detected, quantum cryptography promises unbreakable encryption. Photons are also central to emerging technologies like quantum teleportation, where information is transferred instantaneously across space, and quantum sensing, which could lead to new levels of precision in measurement and imaging. Conclusion: the mysteries of the quantum world. As we conclude our journey through the quantum world of photons, it's clear that light is far more than just a simple wave or particle. It is a gateway to the mysteries of quantum mechanics, a realm where reality defies our classical intuitions and where new possibilities emerge. The dual nature of light as both a wave and a particle challenges us to rethink our understanding of the universe. Concepts like quantum superposition, entanglement, and the role of observation stretch the boundaries of what we know and invite us to explore the unknown. In the years to come, as quantum technology advances, we may unlock even more secrets of photons and the quantum world, leading to innovations that will shape the future of science and technology. Until then, the quantum world remains one of the most fascinating and mysterious frontiers of human knowledge. Thank you for joining us on this deep dive into the quantum nature of light. If you're as intrigued by the mysteries of the universe as we are, don't forget to like, subscribe, and hit the notification bell to stay updated with our latest explorations. See you in the next episode of Sci Discovery Chronicles, where the wonders of science are just a click away.